Hello YouTube. Today we're going to be doing some modern physics actually. So we're going to be dealing with things like special relativity for this example. There are a lot of videos I found on YouTube about the theory of special relativity and relativity in general, but I'd like to apply a problem from a textbook. So to see how you can apply what we know about Einstein's theory of relativity. So say there's Carl on a spaceship, and he's passing by at 0.5 c, which is half the speed of light. So that's how fast the spaceship is traveling. And you are on a planet, and you're watching Carl on his spaceship doing an experiment. That's you. And you look at your watch, and it takes 1 minute. So we'll say that's delta t is 60 seconds. So how much time did Carl spend in his calculation? So in special relativity, you know that as things approach the speed of light, time and length, we'll just talk about those, will change. So there's something called time dilation and length contraction. Well, this delta t naught is something called proper time, and proper time is the shortest possible time between two events. And we know as objects approach the speed of light, time is shorter or moving slower. So that's what we're looking for. Want to know Carl's time. And this formula here is explains one of Einstein's postulates, and this is the time dilation consequence of the postulates. And that gamma on the right, so it says delta t is equal to the proper time times gamma. Well, what is gamma? First, let's apply this to our equation here. So delta tu is our time, which is 60 seconds, is equals to delta t of Carl times gamma. So the u is for u, meaning u, and the delta tc is for Carl, the time for Carl, which is the proper time, since we know by Einstein's theory of relativity that is the shorter time. So gamma is simply how relativistic, quote unquote, the situation is. So if gamma were 2, then that would be the factor in which something is 2 times greater or half as less the original quantity. So for example, if gamma were 2, you know that the length of an object would be maybe half or 2 times as long, and then the time is half or double, something like that, is how relativistic it is. It's what it kind of measures how fast you're going and what that does relativity-wise. So the formula is this: 1 over the square root of 1 minus v squared over c squared. You might see it as 1 over the square root of 1 minus beta squared, and beta is simply v squared over c squared. So for us, we know the speed at which they're traveling is 0.5 c, so you just plug that into the equation, and simplify, you can get rid of the c there, or the c's there. And then you will see that gamma is 1.15. So if gamma were 1, that means pretty much you have classic conditions, you could say, because this relativity really comes into effect for really fast-moving objects, and it's usually just around, I'd say, 30% the speed of light or something. I'm just throwing that out there. So things greater than 1, and gamma's between 1 and infinity. I should have written that down, but I did not. So let's apply this to our equation, plug it in. So we know the time for us observing the experiment is 60 seconds, and we're wanting to find Carl's time, how much has time elapsed on the spaceship, and we just calculated gamma, and we can simply solve for delta tc, and we get 52 seconds. Now, does this make sense? Absolutely. According to Einstein's theory of relativity. Now, it might not make sense intuition-wise, because you're like, how did Carl only have 52 seconds when we recorded 60? Well, this is a consequence of one of Einstein's postulates, and we know that time actually moves our time is longer and Carl's time is slower. So the 60 seconds shows that our time is longer, which is greater than the 52 seconds that we calculated for Carl's time. So here's a very basic example of using time dilation in Einstein's theory of relativity. Hope this helped, and keep practicing.